Hello, my people. Hope we're doing well. The two problems that we're going to be doing in this particular video are special request from Miss Young. She really wants to see the inscribed ones, and those are the more difficult ones. So this one will be dedicated to two of the problems that she asked about on the homework that I'm sure many of y'all also had a question on. So let's go ahead and get started. Find the dimensions of the rectangle of largest area that can be inscribed in an equilateral triangle of side L if one side of the rectangle lies on the base of the triangle. Okay, so let's go ahead and I'm going to do this. I'm going to do at least this in pencil so I don't smudge everything. So if we have a rectangle, and I'm just drawing it in an arbitrary place. It could be in a whole host of different places. I see the fact that when I do this, now remember that this basically angle right here is 60 degrees. This is 60 degrees. This is 60 degrees. That's a right angle, so that's 30 degrees. And all of a sudden, I'm starting to see sort of an angle that I can, not a real angle, but like an approach that I can use in order to actually figure this out. But this one up here is, again, a equilateral triangle. But let's go ahead and drop the altitude down. And that will cut that equilateral triangle into two 30, 60, 90 right triangles, right? So that's 30 degrees, that's 30 degrees, that's 60 degrees, that's 60 degrees, and all of a sudden I have 30, 60, 90 right triangles all over the place, okay? Now what I'm going to do from here is I'm going to start designating variables. Now I'm looking to optimize the rectangle, the area of the rectangle. So I need to find the dimensions of the rectangle of largest area. So let's go ahead and designate this right here as X and this right here as Y. Now when I do that, I notice that this is also X. This right here is also X, this is X, and this is Y. Now 30, 60, 90 right triangles, if you remember, have those necessary relationships in terms of the size, the magnitude of the sides, right? So when you have a 30, 60, 90 right triangle, if the short leg is 1, the longer leg is √3, and the hypotenuse is 2. Okay? Well, that means that if this right here is the shortest leg, that means that this hypotenuse over here is 2x, and this length right here is √3x. Okay. The only problem with doing it with this triangle right here is, of course, the fact that y is on the longer side. Okay? So if y is on the longer side, you don't multiply it by √3 to get the shorter side. You divide it by √3, and to divide by √3 is to multiply by √3 over 3. And of course, this side over here is going to be double that, so it's 2√3 over 3y. Now, I may not need all of this, but all of this definitely could potentially come in handy. Now I know that all of the sides are L, right? So from the corner to the corner to the corner to the corner, they're all L. And so if I want to find a substitution, I could actually take this length right here and say, well, if L is equal to 2x plus 2√3 over 3y, then I could very easily find x in terms of y or y in terms of x. Now x is obviously going to be easier to actually isolate. We could do y too, because remember that √3 over 3 came from the fact that it's 2 over √3, right? It was a rationalized denominator. So if we want to find, well, let's go ahead and do what we had originally said. Let's actually go ahead and find it in terms of x. So we have 2x is equal to L minus 2√3 over 3y, or x is equal to L over 2 minus root 3 over 3y. Well, that's all well and good. That's going to be something that we plug in for x. Now we need the area of the rectangle. Now the area of the rectangle, remember that we designated only half of this side as x. So it's actually 2x times y. And that becomes 2y times L over 2 minus root 3 over 3y. Now, is that a little bit obnoxious? Of course it is. But let's go ahead and find our area in terms of the variable y. Now, I'm going to want to put it in descending order. So let's go ahead and when I distribute the 2y, let's distribute to this one over here first. And I get negative 2 root 3 over 3y squared plus ly. Now, L is unknown, but it's a constant, right? It's basically for any L, okay? Now, of course, the reason why this is no longer a fraction is the 2 and the 2 canceled out when you distribute it. Now, if we have a prime of y, that's going to be negative 4 root 3 over 3y plus L. And of course, we're going to set that equal to 0 and get negative root 3 over 3y plus L is equal to 0, or 4 root 3 over 3y is equal to L. Now remember that this, of course, is 4 over root 3, if we want to change the form of that, which actually is going to be a good idea, because when I divide by this, I'm going to be multiplying by root 3 over 4. And basically, that right there is my critical value for y. That is the y value that potentially maximizes that area. And of course, it's going to maximize it because the way that you minimize the area of that rectangle is you either make y equal to 0, right? You basically shrink it down to a really, really small and therefore not, and then eventually non-existent, basically a rectangle of 0 height, or you basically extend y towards the whole length of that altitude, and then you have a rectangle of 0 width. So just, you know, if you're asked to justify it, right? But, I mean, from here we can tell that that's the only critical value that happens within the interval, and of course, just common sense tells us that it's going to be a maximum. Now, we have our critical value. What is it that we were actually asked? Find the dimensions of the rectangle. Well, I have x in terms of y. All I would really have to do is just plug that back in, okay? So let's go ahead, and I got another sheet of paper here with the problem on it. I see the fact that x is equal to L over 2 minus root 3 over 3y. And if I take this value right here, x is equal to L over 2 minus, and of course, I'm going to change the form of this coefficient to 1 over root 3 times root 3 over 4L. That's going to be L over 2 minus L over 4. So 1/2 L minus 1/4 L is going to be 1/4 L. Now, remember that when we get up here that x was only half of that side. So the dimensions are going to be the dimensions that maximize area are root 3 over 4L by 1/2 L. Okay, and that's the answer. Now the next one was a little trickier, okay, and actually could be done several different ways, but it winds up resulting in the same equation that winds up being differentiated anyway. Okay, so we can let's go ahead and read this. To find the dimensions of the isosceles triangle of largest area that can be inscribed. Now, what we're going to do first is let's find, let's ish the center, okay? So if we have the center here, and then we can go ahead and we'll draw the base first. And then we'll draw the two equal sides. Is that, maybe it ought to be a little bit over here, but we'll kind of, okay. To the extent that it's off, we'll just deal with it, okay? So we have this isosceles triangle. Now, that means that if basically these two sides are the same, then these two angles are the same. And of course, when you drop the altitude down, and let's actually, that was a little bit off, so let's erase that and let's redraw it. Once you drop the altitude down, that's going to bisect that angle up there. Let's go ahead and call that angle right there theta. Now, we have something inscribed within a circle. Anytime you have something inscribed within a circle or a sphere, dollop to donuts, you're going to need to find the center and use the radius in order to figure stuff out. Now, obviously, it already tells you that the radius is important. So let's go ahead and let's try and find, it's probably right about there, okay? So there's the center, or, you know, close enough. And if there's the center, you want to know what? Here's another radius right here. Okay? And then here's another radius over here. Now, there are 3 ways to actually find the area of this. I could actually find the area of these 3 triangles within the triangle and use that. What I'm going to do instead, and I could use Heron's area formula, but what I want to do, actually let's do the 3 independent ones. I think that's actually kind of cool. So here is an R. This is also R, which makes this triangle right here that I've designated isosceles, which means that not only are these 2 sides equal, these 2 angles are equal. Haha. Now, that means that this angle right here is 180 degrees minus 2 theta, and this is also 180 degrees minus 2 theta. If those 2 are 180 degrees minus 2 theta, added together they are 360 degrees minus 4 theta. Okay, these angles down here are what's left of 360 when you do that. Okay, and so what happens is when you subtract these 2 from 360, you're left with the 4 theta, and that means this is 2 theta. That means this is 2 theta. That's a right angle. That's a right angle. This winds up being 90 degrees minus 2 theta. And this is 90 degrees minus 2 theta. Now, not all of this is actually necessary, okay? But, you know, it doesn't hurt to sort of fill this stuff in and basically see what you got. Now, if I was looking for the area of all 3 of these, I would know that basically anytime you have a triangle that's not a right triangle, you can find the area by using area is equal to 1/2 AB sine C, which is basically 2 sides of the triangle and the included angle. Well, the 2 sides of the triangle, if you use the central angle, is going to be R and R. So basically, and these 2 on the side are equivalent to each other. So the area of the triangle, area of the big isosceles triangle, is basically equal to 2 times 1/2 R squared sine 180 degrees minus 2 theta, and then 1/2 R squared sine of 4 theta. Now, this and this obviously cross out, okay? And we can use some identities to basically simplify this down. I'm not going to go ahead and do all of those details, but once I actually get it simplified, it's r squared sine of 2 theta 1 plus cosine of 2 theta. And by the way, I just basically, the shortened version is you use the double angle identity over here and you use the difference identity for sine over here, and then you basically collect terms and factor, and you get this. That, while not enviable, is actually not going to be too bad in terms of finding the derivative, because it's just a simple product rule. The r squared just sort of comes along for the ride, and I'm going to get the first times the derivative of the second, negative sine 2 theta. Don't forget the chain rule, times 2, right? Because the angle measurement is not just the variable, it's the variable with a coefficient. And then, of course, the second, 1 plus cosine 2 theta, times the derivative of the first, which is going to be cosine 2 theta, again, chain rule, times 2. Now, if you distribute this across the 1 plus cosine 2 theta, and then sort of collect terms and factor out and all sorts of fun stuff like that, what we're going to get, and obviously both of these terms, and by both of these terms I mean this first term and this second term, both of those have 2's in them. So we have 2r squared, and what happens is we actually get it down to 2 cosine squared 2 theta plus cosine of 2 theta minus 1. Well, joy of joys, that factors. And I'm going to get 2r squared, 2 cosine 2 theta, okay, minus 1, and cosine 2 theta plus 1. And if you don't believe me that that's the way it factors, just double check it real quick. Now, from here, obviously, we're going to set this equal to 0, okay, in order to find the critical values. And so from this first one, we're going to get cosine of 2 theta is equal to 1/2. From the second one, we're going to get cosine of 2 theta is equal to -1. Well, cosine of 2 theta is equal to -1 when 2 theta, the angle measurement, is equal to pi, or when theta is equal to pi over 2. Okay, well that's not going to work, obviously, okay? But this one will. You get 2 theta is equal to, cosine 2 theta is equal to 1/2 at 2 places. One of them is at 7 pi over 6. That's not going to work. But the other one is at 5 pi over 3. But it's still not going to work. It's still in the fourth quadrant. So 5 pi over 3. But the other one is pi over 3, which gives us a theta value of pi over 6, which, as we know, is 30 degrees. Okay. That means, if you go back to the original, okay, let's go back to the original. That means that if theta is equal to pi over 6, or 30 degrees, that means that this angle up here is 60 degrees. If that's 60 degrees, and this is an equilateral triangle, the equilateral triangle is actually more specifically, the isosceles triangle is more specifically an equilateral triangle. And so basically the area, the triangle of largest area is the equilateral. And it actually asks for the dimensions of the isosceles triangle, but those ought to be easy to get. If basically it's pi over 6, then you could solve for any one of those sides, and you would get the dimensions. Okay, so I'm not gonna do that. I basically have gotten you most of the way there, and basically, well, oh, I'm just a sucker. I'll do it. Okay, So if theta is equal to 30 degrees, this is 60, okay? This becomes 60 degrees. This becomes 30 degrees. And basically that's r. Okay, if r is the hypotenuse, then that short side over there, of course, becomes r over 2. And this over here becomes, since this is going to be twice that, this becomes root 3 over 2r. And of course, this over here is also going to be root 3 over 2r. And basically, you would have an equilateral triangle, okay? That means you have an equilateral triangle of side length root 3r. So there's your dimensions. Now, if you do it by heron-ons, okay, it actually winds up getting to the same equation as if you were doing it by other means, okay? And I can show you the other means if you want. I think it's probably easier to break it up. The other means would require us to use law of cosines, which I'm sure everybody is just absolutely thrilled about. And of course, that would come from, you basically would have to, the triangle, if you redrew it and you drew the triangle like this, right? Basically, you would need to designate an x, and you would have to use the law of cosines. How did I do that the first time? Let's see. Okay. I actually don't know. I'll show you in class if you really want to see it. Like I said, if you have any questions, please shoot me an email. Bye.